Imagine a world where a tiny device can control massive amounts of power with just a small signal. Welcome to the fascinating realm of silicon-controlled rectifiers, or SCRs. SCRs are the evolved form of Shockley diodes, equipped with an extra terminal called the gate, transforming them into powerful amplifying devices. By adding a third wire to the existing PNPN structure, the Shockley diode morphs into an SCR, capable of being latched with a small gate voltage. When the gate is left floating, the SCR behaves like a Shockley diode, latching by breakover voltage or a critical rate of voltage rise. However, applying a small voltage between the gate and cathode forces the lower transistor on, causing the upper transistor to conduct, thus latching the SCR. This method of securing SCR conduction is known as triggering or firing, the most common way SCRs are latched in practice. SCRs are designed with breakover voltages far beyond expected power source voltages, ensuring they only turn on with an intentional gate pulse. Interestingly, SCRs can sometimes be turned off by shorting the gate and cathode or by reverse triggering the gate with a negative voltage. A variant called the gate turn-off Thyristor, or GTO, makes turning off the SCR easier, though it still requires substantial gate current. SCRs and GTOs share similar schematics, with construction details granting the NPN transistor greater control over conduction. Testing in SCR's functionality can be done with an ohm meter, checking for continuity between the gate and cathode. However, this test is rudimentary and doesn't guarantee the SCR's full functionality. A load current test is necessary for a comprehensive assessment. Some SCRs have an internal resistor between the gate and cathode to prevent false triggering from voltage spikes or static discharge. These SCRs require a stronger triggering signal, often found in larger units, and will show continuity in both directions between gate and cathode. Sensitive gate SCRs, lacking this internal resistor, can be triggered by the slightest positive gate signal. A practical test circuit for SCRs uses a DC voltage source and push-button switches to latch and unlatch the SCR. Pressing the on switch connects the gate to the anode, latching the SCR and allowing current to flow from anode to cathode. Releasing the on switch keeps the load energized, while pressing the off switch breaks the circuit, turning off the SCR. If the SCR fails to latch, the issue might be with the load, as a minimum holding current is required to keep the SCR latched. For a comprehensive test, the forward breakover voltage limit and the critical rate of voltage rise should also be tested. SCRs can be used in practical applications like start-stop control circuits for DC motors or as crowbar devices for overvoltage protection. In a crowbar circuit, an SCR placed in parallel with a DC power supply output prevents excessive voltage from reaching the load. SCRs are also used for AC power control, despite being inherently DC devices, by controlling the timing of their conduction. By triggering the SCR at different points along the AC waveform, we can achieve time-proportion power control to a load. A simple circuit with an SCR can control half-wave power to a load, demonstrating the basic concept of time-proportional control. Adding resistance to the gate circuit delays the triggering, reducing the average power delivered to the load. A phase-shifting capacitor can further delay triggering, allowing control over power delivery beyond the AC waveform's peak. More complex circuits, like those using pulse transformers, provide electrical isolation and precise control for industrial applications. In controlled bridge rectifiers, multiple SCRs are used to handle current through both half-cycles of the AC wave. Pulse transformers allow triggering of SCRs with non-common cathode connections, essential for multi-phase power control. Three-phase controlled rectifiers maximize efficiency in industrial systems, using SCRs for